Hello, welcome to Chapter 6, Part 3. In this video lecture, we will be talking about gravity. We're going to focus on two successful explanations of gravity, one by Isaac Newton and the other by Albert Einstein. We will be spending most of our time talking about Newton's law of gravity. I will spend a little bit of time just introducing you to some of the concepts of Einstein's theory of gravity, just because it's so fascinating. So Newton's law of gravity, let's talk about the semantics here. The word law, remember, describes how something behaves in nature. So Newton's law of gravity describes how gravity behaves without an explanation of why it explains that way. For Newton's description of gravity here, we're going to talk about his universal law of gravitation, orbital motion, and also the phenomenon of apparent weightlessness. When we talk briefly about Einstein's theory of gravity, remember in science the word theory explains why. And so Einstein's theory of gravity explains why gravity behaves the way that Newton's law describes it. So we'll talk briefly about some of the different consequences of Einstein's theory of gravitation. So we're going to start our lecture by discussing Newton's universal law of gravity. And there's sort of a famous story, and there's some evidence that the story is at least partially true, that Newton was influenced by watching an apple fall from a tree. And I like to often embellish the story and think that Isaac Newton maybe needed a nap after coming up with his laws of motion and after inventing calculus. So he decided to go outside in the garden and take a little rest under the apple tree. But his rest was interrupted by one of the apples in the tree falling. And, maybe it hit him on the head and woke him up. We don't really know. But needless to say, Newton saw this apple fall. And for most of us, that would just be an everyday occurrence and we wouldn't think twice about it. But Newton wondered why. What made this apple fall to the earth? Some invisible force was pulling the apple downwards. And Newton wondered, could this same force keep the moon in orbit about the Earth? And even going further, could this same force keep the Earth and the other planets in orbit around the sun? Because remember, at this point in time, nobody understood why the planets orbited the sun or why the moon orbited the Earth. The motions were understood very well, but nobody knew the cause of the motion. So it was the genius of Isaac Newton to discover basically this force, which we now call gravity. So what is gravity? Well, gravity is an attractive force between two or more objects. So you can see in the animation here, we have two objects here. And these two objects could be any two objects. One could be a planet, the other could be a star. One could be the moon, the other the Earth, or they could just be two rocks. And let's just say they're out floating around in space. Well, what gravity does is it causes an attraction between these objects because of their mass. So each object is feeling a pull towards the other. And the amount of force that each object feels is exactly the same. Even though one object might be much larger than the other, the amount of force attracting them is the same acting on both objects. And this is a consequence of Newton's third law. Remember that for every action, there is an equal and opposite reaction. So if object A over here is pulling on object B, then object B is also pulling on object A, and those two forces are equal and opposite. One of the characteristics of gravity, and we're going to look at this in more detail in the next slide, is that the larger the mass, the stronger the gravity, which is produced by that mass. So again, even though, basically the amount of gravitational attraction between these two objects, it turns out it's going to depend on both masses multiplied together. But the general trend here is that more massive objects have larger gravity. The other characteristic of gravity is that the closer the objects are to each other, the stronger the gravity. And this kind of makes sense, I guess, in the sense that as you're closer to the source of the gravity, the gravitational pull will become greater. So we'll look at this more quantitatively in the next slide. So one of Newton's greatest achievements was him coming up with what is now called Newton's Universal Law of Gravitation. In words, it's a little bit of a mouthful here, but it says that any two or more bodies attract each other through gravitation with a force proportional to the product of their masses, m1 and m2, and inversely proportional to the square of the distance r between their centers. All right, so here is the universal law of gravitation written out as an equation. So the force of attraction between, we've got object m1 here, mass 1, and we've got another object over here with mass 2. And as we saw in the previous slide, the animation, these two masses are attracted to each other by an attractive force. And the force of object 1 on 2 is the same as the force of object 2 on object 1. So that force is given by this expression here. Notice in the top, we have the two masses multiplied together. Okay, so we take the product of the two masses of the object. You can think of the mass sort of as the source of gravity. So, and the more mass we have, the more gravity we're going to get. This number out in front is g, and this is a very different g than the lowercase g we saw before. This g is called the gravitational constant, and it is a number given by 6.67 times 10 to the minus 11, and notice it carries a bunch of units here, Newton meters squared per kilogram squared. Again, this number is a constant. It doesn't change. This number is a universal constant. It's valid anywhere in the universe, unlike lowercase g, which is 9.8, but that only holds on Earth. This g is universal. In the bottom here, in the denominator, we have r squared. Now, r is the distance between the objects, and specifically, it's the distance between the centers of the object. So if these were two planets, for example, we would measure r from the center of this planet to the center of the second planet over here, all right? And notice that r is squared. Now, what this tells us here is that if we make the distance between these objects greater, remember it's in the denominator, so that means the force of gravity is going to get smaller, all right? And not only does it get smaller, but it gets smaller as the square of the distance, okay? So this is called an inverse square law. The other thing that's really profound about this, and this is the amazing thing about when Newton came up with this law here, he realized that this law is universal, meaning it works everywhere in the universe. And this is a profound statement, because what this is saying basically is that the universe that we live in, the entire universe, obeys a set of laws of nature. And those laws, as far as we know, the same laws apply everywhere in the universe. So this is a great leap forward in understanding the universe that we live in, because the universe basically obeys a rather small set of physical laws. In order to understand a little better how gravity works, let's look at some sort of semi-quantitative, almost conceptual examples which demonstrate how this law behaves and how gravity really behaves. So here's the universal law of gravitation again. Remember this F here, that's the force of gravity between the two objects as shown in this picture here. We have object 1 here and object 2 here, and they are attracted to each other by an equal and opposite force. And r, remember, is the distance between the two objects. So the first question is, if the mass of one object is tripled and the other mass stays the same, how does the force of gravity between the two objects change? You might want to pause the video right now and think about basically what would happen if you made one of these objects 3 times more massive than it is. How would that affect the gravitational attraction between the two objects? So maybe pause the video right now and think about which of these 4 answers is correct. Okay, well, we know that if we increase the mass, we know that the gravity is going to get stronger because that's one of the basic characteristics of gravity. So the answer is either 3 times stronger or 9 times stronger, but we're only changing the mass of one of the objects. So you can think of putting a factor of 3 up here in front of, let's say, m1. So that's going to make the gravity 3 times stronger. So the correct answer is B. The second question is, if both masses are tripled, how does the force of gravity between the two objects change? So again, go ahead and pause the video and think about which one of these answers would be correct. All right, in this case, we have this object being 3 times more massive, and also this object here is 3 times more massive. So they each contribute a factor of 3 in the numerator up here. You can think of a 3 here and stick another 3 in front of this one. So the total effect is we're going to have a gravity force that is 9 times stronger in this case. Now let's look at the distance. If the distance between the two objects is doubled, how does the force of gravity between the two objects change? So again, please pause the video and reason through using the equation here. What happens if we make this distance twice as big? All right, well, to answer this, first of all, the easy part, think about, all right, if we're going to separate these two objects and make them farther apart, is the gravity going to be stronger or weaker? And it's pretty easy to see that, if they're farther apart, right, the attraction is going to be weaker. So the question is, how much weaker? Well, we're making the distance twice as much. So at first glance, we might think, all right, it's going to be 2 times weaker. But remember the fact that the distance is squared. We have r squared down here in the bottom. So the correct answer is 4 times weaker because 2 squared gives us a factor of 4. The last question here is, if the distance between the two masses is shortened to 1/10 the original distance, how does the force of gravity between the two objects change? So go ahead and think about this one. Okay, so now we have the distance between these two masses getting closer together, right? So we know, first of all, that the gravity is going to get stronger, not weaker. The question is how much stronger? If we're making the distance 10 times shorter, remember that we square the effect of the distance. So that's going to make the gravity 100 times stronger. So the correct answer to this one is D. A really useful application of Newton's law of universal gravitation is calculating the Earth's mass. People always wondered, what is the mass of the Earth? And obviously we can't place the Earth on a big scale to measure its mass, so we have to measure the mass indirectly. So we can precisely measure Earth's mass indirectly by using Newton's law of universal gravitation. So how do we do this? Well, remember that the force of gravity is what we call weight. So if we take, here's the Earth right here, and let's say we just take a little object like a ball and we set it on the ground, all right? Well, this ball has weight, okay? And even before we knew about what gravity was, we knew that the weight of an object is equal to mg. So this is m, the b is for ball, so we can make sure we distinguish the mass of the ball from the mass of the Earth. Now, the force of gravity we just learned from Newton's law of universal gravitation to be equal to big G times the product of the two masses. So we're going to take the two masses here to be the Earth and the ball. So here's mb for ball and me for Earth. And then, of course, we have to divide by r squared, where remember, r is the distance between the centers of the two objects. So basically, r here is the radius of the Earth. We have our equation here, and notice the mass of the ball shows up on both sides of the equation, so we can cancel that out. And we're left, interestingly, with an equation for G. And if you plug in the numbers here, if you plug in the universal gravitational constant here, big G, and you plug in, if we knew the mass of the Earth, which we now do, of course, and you plug in the radius of the Earth, you'll get 9.8 here. But that's not what we're going to do. We're going to use this equation here to solve for the mass of the Earth. And let's pretend we don't know what the mass of the Earth is. So the mass of the Earth should be equal to little g times the radius of the Earth squared divided by big G. So we know all these numbers here, all right? Little g, of course, is 9.8. We can measure that very easily. The radius of the Earth, this is something that was well known before we knew the Earth's mass. This was done by geographers and so forth. They could figure out the radius of the Earth was 6.37 million meters. All right, so that's written out here. And then, of course, the gravitational constant down here was determined in laboratories back in Newton's days as 6.67 times 10 to the minus 11. So if we put all this into our calculator, we come up with 6.0 times 10 to the 24th kilograms. And sure enough, this is the correct value for the mass of the Earth. This is 6 trillion kilograms. So obviously, the Earth is incredibly massive compared to everyday objects that we're used to. Another thing that is kind of interesting that comes from Newton's law of gravitation is that we can calculate the acceleration of gravity. This is little g now, and also calculate what our body weight would be on other planets or objects in the solar system. So, remember from the past slide, we said that weight is defined as the force of gravity. So we have mg, m times little g, is equal to big G times m, this was our object again, the mass of the ball or whatever it was, times the planet's mass divided by r squared. And so dividing by m sub b, we end up with an equation here for the acceleration due to gravity. Okay, so this is little g. So if you're wondering, before we said that little g was 9.8, and we actually measured that. I showed you a demo where I dropped some balls and came up with a pretty decent estimate of 9.8. But theoretically, little g comes from this equation here. It comes from the universal gravitational constant, which again is 6.67 times 10 to the minus 11. And then we multiply that by m here, which is the mass of the planet. So for Earth, we just saw that the Earth's mass was 6 times 10 to the 24 kilograms. And then this r down here is the planet's radius in meters. But this equation here works for any planet. It doesn't have to be Earth. Obviously, we can put in a different planet's mass and radius and determine what the acceleration of gravity would be on that planet. So this chart here, or table, shows that, for example, for Earth, of course, little g, the acceleration due to gravity is 9.8 meters per second squared. And let's just say somebody weighs 150 pounds on Earth. I'm using English units here because that's what our bathroom scales measure us by. Okay, now, if we went to Venus, if this person went to Venus, you can see that the G value on Venus is a little bit less. It's close, but it's about 10% lower. It's about 8.9 instead of 9.8. So on Venus, this same person would weigh only 136 pounds, right? They'd be 14 pounds lighter because of the lower gravity. Now remember, a person's mass doesn't change, but the G does here, right? Your weight is equal to mg. All right, on Mars, the gravity is significantly smaller. It's 3.7 meters per second squared. So this person would weigh about 57 pounds on Mars. And the moon, we saw the video earlier with the astronauts dropping the hammer and feather. The moon's gravity is about 1/6 of what it is on Earth. So a person would weigh only about 24 pounds on the moon, which is kind of interesting because the astronauts found that they could move around on the moon more easily by hopping, kind of like a bunny rabbit. They would hop on 2 feet, and because of their light weight, they could actually just bounce around on the moon. It was more efficient than walking. The other thing regarding those astronauts is they wore backpacks, basically, that had their life support system, their oxygen and all that stuff. Those backpacks weighed about 300 pounds. And you might wonder, well, wow, how could they, walk around on the moon with a 300-pound backpack? Well, that was 300 pounds on Earth. But on the moon, that pack only weighed about 50 pounds, which is like a heavy backpack you might wear while hiking on the Earth. All right, now let's go the other direction. On Jupiter, G is 23. So this 150-pound person on Earth would weigh about 350 pounds on Jupiter. And if you could stand on the surface of the sun, even though the sun does not have a solid surface and it's awfully hot, but if you could, you would be experiencing a G, acceleration due to gravity, of 274, meaning you would weigh 4,200 pounds. So that would almost certainly snap all the bones in your legs. You would not be able to stand up because of your incredible weight. And just to take things to the total extreme here, there are objects in space called neutron stars, where the acceleration due to gravity is about 2 trillion, meaning your body weight on a neutron star would be about 28 trillion pounds. This gravity here is so extreme and intense that it would tear your body apart, and even all the molecules and atoms in your body would become completely ripped apart by this gravity. So my message here is don't sign up for a vacation to visit a neutron star. It would not be a pleasant visit. Haha. Let's take a look now at orbital motion. Isaac Newton came up with a thought experiment where he imagined placing a cannon on top of some hypothetical really tall mountain on the Earth. All right, so this is an imaginary mountain. In fact, this mountain is so tall that it actually sticks up above Earth's atmosphere. So the top of this mountain is up sort of in a vacuum, okay? So, Newton imagined taking this cannon and pointing it horizontal, okay, not up or down, but straight out sideways, and firing the cannon off of this mountain. And, what would happen here is the cannonball would shoot out of the cannon and it would come down and fall and hit the Earth somewhere below. So Newton realized, what happens if we make the cannon a little more powerful and shoot this cannonball out a little farther? Well, now the cannonball, since it's going faster, it's going to travel farther before it comes down and crashes onto the Earth. But taking this to the extreme, Newton realized that if he had the speed just right, he could shoot this cannonball, and as the cannonball was falling towards the Earth was curving away from the cannonball's path at the same rate. So even though this cannonball is falling, it's never getting any closer to the Earth. And in this case, this cannonball would come right back around, and I guess if Newton didn't duck, it would hit him in the back of the head, right? But assuming that he ducks, this cannonball is just going to keep going around and around. This is an example of basically a low Earth orbit. All right, Newton had just realized how an orbit works. So taking this then a little bit further, if this cannonball is shot with even more speed, what happens here is instead of the orbit being a perfect circle, the orbit will start to become more elliptical, kind of oval shape. And given enough speed, the cannonball could actually escape Earth's gravity completely. All right, and that's something called the escape velocity, which we'll maybe talk about a little bit later in the course. So before we get into the orbit equation, one way to visualize an orbit, so this is, let's take a planet that's orbiting around the sun in our solar system, okay? And the reason it's shown like this in planetary orbits are actually elliptical. They're not nearly as the elliptical is shown here, but this is just sort of to show the effect. The idea of an orbit is that the planet is moving, obviously, and its momentum, which has to do with its velocity, wants to make the planet fly off into space. But of course, gravity is an attractive force between the sun and the planet. And the gravity always points inward towards the sun. So no matter where the planet is, gravity is pulling it, wants to pull it towards the sun. So what happens here is this gravitational attraction here causes the planet to curve in its path. And basically what happens here is this gravity is a centripetal force, right? We learned about this in the previous chapter. And this centripetal force ends up causing circular motion, okay? Or in this case, an elliptical motion. And the result is a stable orbit. You can think of this planet in a sense falling towards the sun, but it never does. It never, the orbit does not decay in normal circumstances here. So the other thing, one of the effects here, which we're not going to really deal with in our physics class, is that as the sun gets, the planet gets closer to the sun over here, it starts to speed up because in a sense it is falling towards the sun. But then when it comes around here, it's sort of going up, away from the sun, and it slows down to its slowest point in the orbit. So this is just sort of a conceptual explanation of how an orbit works. The planet, would tend to fly off into space in a straight line, but the sun's gravity is pulling the planet and curving its path, creating this orbit. As I mentioned in the last slide, if we think of an orbit, it's actually another really nice example of circular motion. And if we think of a circular orbit like this, basically the planet would be in uniform circular motion, which was, of course, the topic of one of our previous lectures. So remember, whenever we have uniform circular motion, like, for example, the Earth orbiting around the sun like this, we know there must be a force that points towards the center of the circle that causes the circular motion. And in this case, of course, that force is gravity, right? It's the gravitational force between the Earth and the sun that provides the centripetal force. So remember Newton's second law for centripetal forces. We have the centripetal force is equal to ma, F equals ma, but here our acceleration is centripetal acceleration. So we can replace the centripetal force here with the gravitational force. So this is Newton's law of universal gravitation. The mass of the planet is mp, and the mass of the sun is m sub s. All right, so in this picture I'm showing the Earth, so this would be the Earth's mass we would plug in here. On the right side, this m, remember where that's this guy here. We're talking about this body that's orbiting around the sun. So, and this little m here, we're going to replace with the mass of the planet. And then the centripetal acceleration, remember, is given by v squared over r. We learned about this in the last chapter. So what we can do now is clean up this equation a little bit. We've got the mass of the planet on the left, and we've got the mass of the planet on the right, so we can cancel those out. And interestingly, it doesn't the orbit doesn't depend on the mass of the planet, only on the mass of the sun, because the ms here remains. The next thing we can do is notice that down over here we have r squared, and over here we have r, so we can actually multiply both sides by r, which will get rid of this r, and it'll get rid of the r square and just turn it into a regular r. So what we've done then is we've basically solved this equation for v squared. So this is called the orbit equation. The velocity squared, or speed squared, of the planet is equal to big G, all right, this is the gravitational constant, times the mass of the sun divided by r. And remember, r is the radius of the orbit. So this would be the distance between the planet and the sun. And what this equation really is it's a relationship between the speed and radius of an orbit of a planet around the sun. Let's look at an example of the orbit equation for the planet Earth. So we're going to calculate the speed of the Earth as it orbits the sun. The sun's mass is given to us here as 2 times 10 to the 30th kilograms. Obviously, that's a big number, right? The Earth's orbit radius is 150 million kilometers, or in scientific notation, that's 1.5 times 10 to the 11 meters. So here's the orbit equation stated right here. And we're going to basically solve this for v. So we can take the square root of both sides here and just plug in our numbers. So here's the value of g, big G. Here's the mass of the sun, and here's the radius of the Earth's orbit. And when you do all this on your calculator, you come up with an answer of about 30,000 meters per second. If you do the conversion there, by the way, that's 67,000 miles per hour. So that's how fast our Earth is traveling around the sun. So it's kind of interesting to think about that right now. As you sit there at your desk or table, we are actually traveling through our solar system at 67,000 miles per hour. This answer can be checked using some methods that we learned in the previous chapter on uniform circular motion. The speed of an object is equal to the circumference of the circle divided by the time or the period. And converting all the units and everything here, it checks to, of course, give us the same answer of 30,000 meters per second. The orbit equation can be easily modified to apply to other situations. For example, for a satellite orbiting the Earth, the only thing we have to change here is that instead of the mass of the sun being the source of the gravity here, now it's the mass of the Earth, since the satellite is orbiting around the Earth. The other thing we have to be careful if we're going to use this is that the r, remember r is the distance from the center of the two objects. And so in this case, basically r starts from the center of the Earth, goes up to the surface of the Earth. Now that's the radius of the Earth, but then we have to go upward till we get to the satellite. So r would be the radius of the Earth plus the altitude of the satellite above the Earth's surface. But when those modifications are made, this equation here can be used to calculate the orbit parameters, the velocity and the radius for satellites. One of the interesting consequences of orbit is this concept of apparent weightlessness. And this comes from the fact that if we take a scale and hang an object from a spring scale, this scale will read the object's weight, of course. But if we drop the scale and let the scale and the object fall together, well, then the object is not going to be pulling on the scale anymore because they're falling together. Now remember that when an object is in orbit, it is really in free fall. It's literally falling to the Earth, but remember, because it's moving around the Earth, it never comes down. It's just the Earth's surface is curving away from the path of the falling object. But for anything in orbit, it's in a state of apparent weightlessness. So this is why we see astronauts floating around inside the space shuttle or the space station. There is gravity where they're at. There is gravity, but they are in a state of free fall because they're in orbit. So they don't, basically, they don't experience the gravity, they're experiencing weightlessness. Let's finish up this lecture on a little bit of a different note here. No discussion of gravity would be complete without mentioning Albert Einstein. Your textbook has a chapter on Einstein's special theory of relativity later in the book, and it's not part of Physics 101, but if you take Physics 102, you may study that in that course. I just want to briefly introduce Einstein's contributions to the theory of gravity. His theory of gravity is called the theory of general relativity. Einstein is often regarded as the greatest scientific genius that ever lived. He became a celebrity, and his wild-haired appearance became the iconic look of a mad scientist. But it's interesting to know that almost all of the major work that Einstein did was done when he was a young man, and he looked like this fella up here, pretty normal-looking guy. So Einstein's theory of general relativity is an extremely complex theory, and in fact, it took Einstein 10 years to figure it out. And, you know, that was maybe one of the smartest people that ever lived. It took him that long. So we're not going to, you know, do any justice to it here, but I just want to give you a few of the sort of major concepts of his theory without getting into all the math and everything. One of the things that sort of tipped Einstein off to understanding what gravity is that there are two masses that we've seen so far in our equations. We've seen gravitational mass and we've seen inertial mass. So gravitational mass, remember Newton's universal law of gravitation, has mass in it. Well, so does Newton's second law of motion, F equals ma. Now these two masses here have, you know, they look like they're very different. One is causing gravity over here, and this one is in what's called inertial mass. Remember, this is just the resistance for something to accelerate. Einstein realized that somehow, because these masses are the same in both equations here, one has to do with gravity, the other has to do with acceleration, is that gravity and acceleration are linked together and they're related because they depend on the same mass. So this led Einstein to this idea of what is now called the equivalence principle. It basically states that the effects of a gravitational field are equivalent to acceleration. So here again, we're seeing this link between gravity and acceleration. In a closed laboratory, there is no way to distinguish between gravity and an acceleration of the lab itself. So to show you what this means, imagine you're inside of a closed box here, and you're not allowed to look out the window, and you have no idea where you are. Okay. Now it just so happens that this box or laboratory that you're in is sitting on the Earth. So if you do an experiment inside your laboratory, for example, you drop a ball and time it and so forth, you will come up with an acceleration of 9.8 meters per second squared when you drop something, and you will say, okay, I must be in a gravitational field. However, if instead this same lab was inside of a spaceship, and this spaceship was out in deep space where there's no gravity, but the ship's engines were firing, and you are accelerating at precisely a value equal to g. In other words, 9.8 meters per second squared. Now, if you're in this lab, you would feel the same effect as you were sitting here on Earth. If you dropped a ball, that ball would accelerate down to the floor at 9.8 meters per second. You would have weight, and all the laws of physics would be the same. So in other words, you could not tell whether you were in a ship on Earth or in a ship accelerating at 9.8. There's no experiment that you could do to prove you were in one or the other. Furthermore, if you were on Earth and you were in a ship and you were free falling toward the Earth, you and all the objects inside of your lab would be floating around. All right, this is the same as orbit, right? We saw the astronauts in the space station orbiting the Earth. The same thing would apply if you were just floating out in deep space without any gravity nearby. You would also be floating around inside your lab. And again, you would have no way to tell whether you were free falling toward the Earth here or just floating in deep space. So this was called the equivalence principle. So amazingly, this equivalence between a gravitational field and acceleration leads us to one of the consequences of Einstein's general relativity theory, and that is that gravity has to do with the curvature of space. And again, this is not a simple thing to explain, but one demonstration that sort of shows the concepts might help clarify this. So suppose you're in your closed lab here, and you're either, let's say first you're floating out in deep space where there's no gravity. So if you were to shine a laser beam across your lab, the light beam would of course go in a straight line, as light always follows the shortest path between 2 points. Now remember that by the equivalence principle, we can also take this same lab and we can let it fall towards the Earth. And if you're inside there, you can't tell the difference, okay? So as you're falling, this laser beam inside the lab here would go straight across. But now if we take this and observe the same effect from the Earth's frame of reference, or at a different point of view here, we would see that when the light beam left the laser here, the lab was up here, and remember this light beam is going to start going across the lab, but the lab is falling down. So by the time the light beam, gets to the other side of the lab has dropped down to here. So we see actually this light beam following a curved path through space. And kind of going forward here, since light always follows the shortest distance between 2 points, the space around the Earth's frame of reference must be curved. So this sort of leads to Einstein's idea of gravity. Newton viewed and modeled gravity as a force between massive objects, but couldn't explain why that force exists. Einstein viewed space, the 3 dimensions of space, and time as a 4th dimension, and space and time are woven together. This is often called the fabric of space-time. Einstein explained gravity as a curvature of space-time. And basically, massive objects curve the space-time around them. So, for example, if you take a piece of graph paper to represent flat space and technically space-time, when you have a massive object in the vicinity, all right, in this region of space, it's like you took a bowling ball and laid it on top of your bed. It puckers or warps the space-time around it. Okay, and so this is one way to sort of visualize what curvature of space means. And then if we take, let's say, a marble, and this is your bed again, right, with the bowling ball in there, and we roll a marble across the bed, well, it's going to actually be, the path of the marble is going to be curved because of this curvature in the space-time. And this marble may actually, if there was no friction, it could actually just keep spinning and orbiting around this massive object. So the curvature of space-time affects the way that objects move through space. So this was the first time that gravity could be understood as why it's an attractive force. It's because of this curvature in space-time. One of the consequences of Einstein's theory was the deflection of light as it goes around a massive object. And Einstein's theories correctly predicted the precise amount of deflection of starlight as it passes near the sun. So, actually when starlight passes by the sun, the beam of light is curved. And so it gives us a different apparent position from where the star actually is. And taking this to an extreme, astronomers have used clusters of galaxies like this. Each one of these fuzzy blobs in this picture is a galaxy like our own Milky Way galaxy containing hundreds of billions of stars. There's so much mass in this cluster of galaxies that any object behind the galaxy cluster, their light gets curved and actually bent and focused like a giant lens in space. So you can see these streaks of light in this picture. There are multiple streaks. This is due to the distortion of those light waves as they bend and warp coming around the curved space from this cluster. And these are some other pictures here showing gravitational lenses due to galaxy clusters. Black holes are one of the most fascinating objects in the universe, and it's one of my favorite topics in the astronomy classes that I teach. But we don't really have the time here to talk about them in any detail, but you can sort of visualize a black hole as a bottomless pit in space-time. So remember this idea of, you take your nice soft bed and you place a bowling ball on it and it warps the surface of your bed. That's sort of our analogy for curved space-time. Well, what a black hole is if you put something on your bed that was so heavy that it actually curved down, your bed curved down and made a bottomless pit with no bottom to it, right? This is an infinitely deep hole. That's sort of how to visualize a black hole. So the space-time around it is so severely curved that nothing can escape, not even light. That's why it's called a black hole. In fact, remember that space and time are woven together. Time is just one of the dimensions. And the curvature is so great that time actually comes to a stop around the surface of a black hole, which is a very difficult concept to try to comprehend. We don't actually see the black hole because light can't escape from it, but we can detect the X-rays that are emitted by gases that are superheated as they fall into the black hole. So in this artist's rendering here, we see a black hole in the center here, and this is the remains of maybe a star or something like that. That is basically all the matter here is swirling around and getting sucked into that black hole. But as it falls into the black hole, the gas is superheated to millions of degrees and it emits X-rays. And we can see those X-rays with X-ray telescopes. This is a radio telescope image of a black hole. One of the other fascinating predictions of Einstein's theory is something called gravitational waves. So gravitational waves are ripples in space-time. Now, to kind of, again, get a grasp of what this means, imagine that, you have a nice calm pond here, or maybe a swimming pool, and there's a couple of bugs swimming around or fluttering on the surface of the water. And of course, the disturbance there creates little waves or ripples, and those ripples travel away from the disturbance in the surface of the water. Well, the gravitational waves are in a sense like that, but what is actually waving? Well, on a pond, obviously it's the water that is waving and wiggling. But for gravitational waves, it's space-time that is actually rippling. So how do you imagine that? Well, this is, again, you can kind of see the graph paper here, and this is representing space and time, which has these outward going ripples. So 100 years after Einstein predicted the presence of gravitational waves, we finally had the technology to directly detect them. And the detector was called LIGO, the Laser Interferometer Gravitational Observatory. And just a few years ago, the first gravitational waves were actually discovered. And the way this interferometer works is a laser beam is shot through this arm here of the system, and this is called a beam splitter. One part of the beam is sent this way, the other part of the beam is sent this way, and you can see the size of these tubes here that carry the beams. They're miles long, and inside those beams are then bounced off of mirrors and recombined, and the beams basically interfere with each other. And if this thing is all lined up and there are no gravitational waves present, they can detect a certain level of brightness from the interference of these beams. Now, if a gravitational wave comes along, remember what that does is it ripples space-time. So it actually shortens and lengthens the lengths of these arms, and they can measure that by looking at the interference pattern of the light waves. And these ripples are they're microscopic, basically. So they're just tiny little altercations or changes in the lengths of these arms here, and those manifest themselves as light and dark regions in the beam, which is detected by this photodetector. So anyway, that's our last slide here. So hopefully you at least got a little bit of a sense of Einstein's theory of general relativity and how it explains gravity. Until then, we will move on to the next chapter. We'll see you then.